Hello everyone. In this video, we will see the Eisenstein criterion. So let us look at the statement of the Eisenstein criterion. Let P be a prime and suppose that f of x is equal to an x raised to n plus etc plus a naught is in z of square bracket of x. That is a polynomial f of x which is equal to an x raised to n plus etc plus a naught have all the coefficients which are integers. Next we can see that an must be not congruent to 0 mod p. So if I write out the coefficients of this polynomial, that is an etc a naught, the first condition is that an is not congruent to 0 mod p, where all other ai's are congruent to 0 mod p. Now this a naught has the additional condition that this a naught is not congruent to 0 mod p square. So if I write out the conditions once again, we have an is not congruent to 0 mod p and this a naught is congruent to 0 mod p, and the additional condition is that a naught is not congruent to 0 mod p square. Then we need to prove that f of x is irreducible. So let us assume that f of x is not irreducible. So we write, that is, let us assume that f of x is reducible, which means that it is possible to write f of x as a product of two polynomials whose degrees are less than that of f of x, that is less than n. So let us take one of the polynomial as cs x raised to x plus etc plus c naught, and the next polynomial as br x raised to r plus etc plus b naught. So if I write out the assumption more clearly, we need to write that f of x is not irreducible, that is f of x is reducible. So if f of x is equal to product of these two polynomials, we need to assume that this r is strictly less than n and s is strictly less than n. And besides, we have cs and br are not equal to 0 in order to show that the degree of the first polynomial is s and the degree of the second polynomial is r. Now, since there are only two polynomials on the right hand side, we have s plus r equal to n, that is, we can have an which must be equal to cs into br is not congruent to 0 mod p. Now this implies that none of them can be congruent to 0 mod p, that is cs is not congruent to 0 mod p and br is not congruent to 0 mod p. Thus we have an is the only coefficient in f of x which is not congruent to 0 mod p, and now we have cs is not congruent to 0 mod p and br also not congruent to 0 mod p. Now if I start from the second condition, that is a naught is which is equal to c naught into b naught is congruent to 0 mod p, then we can say that at least one of the c naught or b naught is congruent to 0 mod p. That is, at least one of c naught b naught, c naught comma b naught is congruent to 0 mod p. Now if I look at the last condition, I have again a naught equal to c naught b naught, which is not congruent to 0 mod p square, implies that both of the c naught and b naught, both of them cannot be congruent to 0 mod p. So you have c naught and b naught, at least one of them must be congruent to 0 mod p, but both of them cannot be congruent to 0 mod p. So if I consider these two statements together, what we can do is that we can put one of them not congruent to 0 mod p and the other congruent to 0 mod p. So let c naught be not congruent to 0 mod p and b naught is not congruent to 0 mod p. So far we have an, cs, br, c naught are not congruent to 0 mod p and b naught is congruent to 0 mod p. Now if I look at the second factor, you can see that B naught is congruent to 0 mod P, where the leading coefficient BR is not congruent to 0 mod P. That is, if I move from B naught to BR, that is B naught, B1, etc. BR, you can find some BM which is congruent, not congruent to 0 mod P for the first type. Remember that Bm is the coefficient of x raised to m, and it is the first coefficient. If I come from B0 to Br, first coefficient which is not congruent to 0 mod P. So how can you write that properly? That is how to introduce m. Yes, let m be the smallest k. So you can choose m to be the smallest k such that bk is not congruent to 0 mod P. So if you are coming from B0 to Br, this k says that it is the smallest, m says that it is the smallest k says that bk is not congruent to 0 mod P. So this means that Bm can be any number that is less than or equal to r. That is, since we already have r is strictly less than n, and you can add a condition, one more statement, that you have this m is less than or equal to r. So we have m less than or equal to r, which is strictly less than n. So let m be the smallest case such that bk is not congruent to 0 mod P. So this means that all these B0 to Bm, that is B0, B1, B2, etc. up to Bm minus 1 are congruent to 0 mod P. And what about Bm? Bm is not congruent to 0 mod P. Now we can consider Am. So what is Am? Am is the coefficient of x raised to m in f of x. So if you look at Am, you know then how to calculate Am. It is the product of the two polynomials on your right hand side, and you can have an expression if the polynomial on the right hand side is defined properly as an infinite sum. So if you have the right hand side, the two polynomials on your right hand side are available as two infinite sum, you can easily find out Am as am is equal to summation from I equal to 0 to m and c I and b m minus I. That is, you need to start with c naught bm plus c1 bm minus 1 plus etc. up to cm and b naught. So here you can see that bm minus 1 up to b naught are available to us. So let me write the last term like as cm and b naught. So bm minus 1 etc. b naught are available in the second polynomial. But if you look at the first polynomial, there is a choice for cm. That is, you can see that cm can appear on the left hand side of cs or on the right hand side of cs. So you can see that cs appears on the right hand side of cm if m is less than or equal to s, and it appears on the left hand side of cs if m is greater than s. So you can have two endings for this expression. That is, if cm appears on the right hand side of cs, you can write that is equal to cm b naught if we know that m is less than or equal to s. Now for the second case, we can see that in any case we can always write it as cm b naught, but if cm appears on the left hand side of cs, we know that this expression, the infinite sum on your left hand side, has all the coefficient equal to 0. So it is enough to take the sum up to cs. So you can end up at cs b m minus s. So that the sum of the suffixes is equal to m. So this condition holds if m is greater than s. Now let us look at the coefficients b0, b1, etc., bm minus 1 once again. We know that all these coefficients are congruent to 0 mod p, and you can see that these coefficients appear here also. That is, you can see that b0, you know that is already congruent to 0 mod p, bm minus s or bm minus 1 up to bm minus 1 all are congruent to 0 mod p. And if you look at bm and c0, which is the only remaining term on the right hand side. So if you look at bm and c0, you know the corresponding conditions that we have. You already know that this bm is not congruent to 0 mod p. And what about c0? You already know that c0, we have taken c0 to be not congruent to 0 mod p. So c0 and bm are not congruent to 0 mod p, which means that the product c0 bm is not congruent to 0 mod p, and all other terms are congruent to 0 mod p. So which means that this am must be not congruent to 0 mod p. So therefore we can write am is not congruent to 0 mod p. Now what we know about the coefficients of f of x? We know that an is the only coefficient. We know that an is the only coefficient that is not congruent to 0 mod p, and all other coefficients are congruent to 0 mod p, which implies that this am must be an. That is, this m must be equal to n. So if you look at this statement, you can see that m less than or equal to r less than n is available to us, and then this m must be equal to n implies that from that inequality m must be equal to r, which must be equal to n. So from that what we have is that this r is equal to n. Now what is r? R is the degree of one of the polynomial, and we now, our assumption that r is strictly less than n, but we have now r is equal to n, and this is a contradiction to our assumption that r is less than n. So we write it as this is a contradiction to our assumption, and hence we must have f of x an irreducible polynomial over Q. Now let us see an example, an application of the Eisenstein criterion. So we are going to show that this polynomial is irreducible over Q. So if we choose P is equal to 3, then we can see that the leading coefficient is not congruent to 0 mod P, and all other coefficients are congruent to 0 mod P. In addition, the last term, that is 12, is not congruent to 0 mod p square, that is not congruent to 0 mod 9. So we can see that this polynomial, that is f of x is equal to 25x raised to 5 minus 9x raised to 4 minus 3x square minus 12, which is a polynomial in z of x, satisfies Eisenstein criterion for p is equal to 3. So which means that it is irreducible over Q. Now we are going to discuss the converse of the Eisenstein criterion. So what is Eisenstein criterion? Once again, f of x is a polynomial with the coefficients from z, and there exists a prime number p such that an is not congruent to 0 mod p, and all other a's are congruent to 0 mod p, and a0 is not congruent to 0 mod p square, implies that f of x is irreducible over Q. Now irreducible in Q of x. Now what about the converse? If f of x is irreducible in Q of x, then there exists a prime p satisfying these conditions. So this is the statement of the converse. Now we need to check whether this converse is always true. So if you look at different problems, you can see that there are examples where this converse is not true, and hence we can state that this converse need not be true always. So for we can see that this x square plus 1, this is a polynomial in z of x, and it is irreducible in q of square bracket of x. So this is a polynomial in z of x since all the coefficients are integers, and you can see that there is no factors possible in q of square bracket of x, which means that it is irreducible in q of square bracket of x. And can you find a p satisfying this condition? All these conditions? No. We cannot find any prime number satisfying all the conditions on your left hand side, which means that there is no such p, prime number p exists. So this is a proof for the statement that the converse of the Eisenstein criterion need not hold always. We now consider a problem which is an application of Eisenstein criteria. So here capital phi p of x is a polynomial x raised to p minus 1 over x minus 1, which is equal to x raised to p minus 1 plus etc. plus x plus 1. We need to prove that it is irreducible over q for any prime p. So you can see that these two expressions are the same. For if you multiply x minus 1 with the expression on the right hand side, you can see that you are going to get x raised to p minus 1. In order to prove this, we start with the capital phi p of x plus 1. That is, consider capital phi p of x plus 1. So on your right hand side, you are going to get, that is, just replace x with x plus 1. So you get x plus 1 raised to p minus 1 by, again replacing x with x plus 1, you can see that it is x plus 1 minus 1. So it is clear that I have obtained this polynomial phi p of x plus 1 from the old polynomial capital phi p of x by replacing x with x plus 1. So you can consider it as an evaluation homomorphism, say phi x plus 1. So phi x plus 1 is an evaluation homomorphism which replaces x with x plus 1, and clearly that is a homomorphism from q of square bracket of x to q of square bracket of x. So now let us consider this polynomial phi p of capital phi p of x plus 1 once again. On your right hand side, if you use binomial theorem, you can see that x plus 1 all raised to p is x raised to p plus p choose 1, then x raised to p minus 1 into 1, and so on. You can have the coefficient of x raised to p minus r as p choose r into x raised to p minus r plus etc. The last term is x plus 1, but there is a minus 1, so you can stop at x, and in the denominator you can have your x plus 1 minus 1, that is x. So we have the coefficient of x raised to p minus r is p choose r, which it is equal to p factorial by r factorial into p minus r factorial. So if you want to look at the coefficient in the numerator except for the first term, so let us choose if 0 less than r less than p, then clearly you are considering all coefficients except the first term. You can see that p divides the numerator of p choose r, and p does not divide neither r factorial nor p minus r factorial, which means that p divides p choose r for 0 less than r less than p, which means that p divides all the coefficients except for the first term that are in the numerator. That is, p divides p choose 1, p choose 2, and so on up to the last term, all the coefficients. So you have all coefficients are congruent to 0 mod p except for the first term, and the first term has the coefficient 1 which is not congruent to 0 mod p. Now what about the last term? Last term has the coefficient 1 which is not congruent to 0 mod p square. So even though you are dividing it with x, the coefficients are the same, which means that phi p of x plus 1 satisfies the Eisenstein criteria, and hence it is irreducible. Now what is our problem? We have proved that 5p of x plus 1 is irreducible. But what is our problem? Our problem is that this 5p of x, we need to prove that 5p of x is irreducible. So what we are going to assume is that we are going to assume 5p of x is not irreducible. So what happens? We are going to get a contradiction. So here, if 5p of x is not irreducible, then we know that you can write capital 5p of x as a product of two polynomials whose degrees are less than that of 5p of x. So if I write 5p of x is equal to, say, some f of x into h of x, where the degree of f of x and h of x are strictly less than the degree of 5p of x, and they are from capital Q of x. Now if I apply the evaluation homomorphism phi x plus 1 on both sides, then you are going to get 5p of x plus 1 is equal to f of x plus 1 into h of x plus 1, just by replacing x with x plus 1. But this expression is not possible, since this expression shows that capital 5p of x plus 1 is a product of two polynomials whose degrees are less than that of capital 5p of x plus 1, and that is not possible since capital 5p of x plus 1 is irreducible, since it satisfies the Eisenstein criteria. So it means that capital 5p of x can also be not written in the form f of x into h of x, so that expression is not also possible. Hence it is not possible to say that capital 5p of x is not irreducible. So we have completed the proof, and this is an application of Eisenstein's criterion. Thank you.